Okay, so we reviewed finding the quartiles. So let me give you another set of data, and I want you guys. All right, so let's say Mr. and Mrs. Jones have 10 grandkids, and the ages of the grandkids are 5, 9, 1, 4, 12, 16, 7, 22. So these are the ages of 10 grandkids. Okay, so I want you to find the median, find Q1, and find Q3.
7 is the bottom.
10. So, yeah, I'll just slide this up here.
I can see it now.
Can everyone see the 10 ages?
It was blocked.
Ages of the 10 kids. Find the median, Q1, and Q3. Alright, you guys need another minute, or are we okay? We're good. Okay, median is 8. Q1 is 5, and Q3, 12. So what we got? Okay. If we did not get that, I will list these out. First step is to put them in order from least to greatest. I have 1, 4, 5, 7, 7, 9, 10, 12, 16, 22. Okay, that's 10 ages put in order from least to greatest. Finding the median, I got 10 numbers, which means 5 numbers are going to be smaller, 5 numbers are going to be larger. So where would I draw my median for the line?
In the middle.
Right here. And so my median is equal to 8. Good. Now to find Q1 and Q3, what do I do to find Q1? I take half of my list and I find the median of these 5 numbers. And where's that?
5.
5, right here. This is Q1. Do the same thing on this side. Find the median of these 5 numbers, and what do I get? 12. This is Q3. Questions? All right. So we can find the median, we can find Q1, we can find Q3. If I ask you to find the mean, you could do that as well, right? You would just do what? Add them up and divide by 10. We have a question? You do another example? Yeah, I'm sorry. I gotta keep going on here. We've got too much stuff to do another example. So you got homework exercises for additional examples. All right. So these again are the median and the mean are numeric summaries for center. Numeric summaries for center. We have the median and we have the mean. Okay. We also have numeric summaries for spread. Actually, before I get into that, let me show a box plot. Okay, so a box plot is another graphic display. Okay, so we've already covered 2 graphic displays for numeric variables. What are they? A dot plot and histogram. Okay, so box plot is a third one, and a box plot has a number line. Okay, a box plot, and it has a box. Okay, as we might imagine. And the box has a line going through it. And from the box we have lines extending like so. So actually let me extend my text. Okay. The box itself is defined by 3 lines. We have a line at Q1, a median, and the line at Q3. Okay? So if I'm using the same data of the 10 grandkids, my Q1 is 5, my Q3 is 12, and my median is 8. And that is where I've drawn the edges of the box. Okay? I have a line at 5, a line at 12, and a line at 8. That forms the box. And then from the box we have what we call whiskers, and they extend to the smallest and largest points in our data that are not outliers. Okay? So these lines, these are whiskers. This is a whisker. And it goes to the smallest, whiskers extend to the smallest and largest points in our data that are not outliers. Okay.
Repeat that one more time. Whiskers extend.
They extend to the smallest and largest point points in our data. But as long as they are not outliers. Okay. We haven't talked about how to identify an outlier, and we won't even bother teaching that, okay? But basically, the lines go out to the smallest and largest data points in our data set. Okay? So the smallest age in my data set is 1, the largest data set is 22, and so the whiskers go down to 1 and 22. Okay? we have rules for identifying outliers, but it's not as critical that we learn them. Basically, if we have a large number, okay, let's say the last number was not 22, but was 32, okay, and I told you that 32 is an outlier for our data set here, okay. Well, in this case, how far would my whisker go? It would go up to 16, because that's the largest data point in my data set that's not an outlier. Okay? So my whisker would go up to 16, and then 32, I would have to go, 32 would be represented with a circle. So that, my box plot's getting all messed up here. But basically, if it's an outlier, it gets represented with a dot, and it's not attached to the whisker. So outliers, so on box plots, outliers are not connected to the whisker. They are represented with a dot. Is that okay? Sure. So if you were to be presented with a box plot, you would be able to identify Q1, the median, and Q3. Yes? Okay, because those would be where the box lies. How much of the data is between 12 and 5? Half of the data. Because 12 represents Q3, 5 represents Q1, and we know that half of the data is between Q3 and Q1. Is that okay? How much of the data is smaller than 5? 1/4. Because 5 is the Q1, first quartile, and we know that 1/4 or 25% of the data is smaller than Q1. Is that also okay? Good. Okay, so that is a box plot. And now I want to talk about numeric summaries for spread. Yes?
What would be the maximum numbers for box?
The largest point would be, in this case, 32. Okay? So even if it's an outlier, it's still part of our data, and that would be the maximum. Okay? So over here, okay, so this would be the max. So even though it's an outlier, it's still part of the data. That's 32. Okay? What's the minimum in our data? 1. Okay, so the whisker goes down to here, so our minimum here is 1. Here, I'll just try another simple exercise. Okay. What's the largest point in my data? 10. The maximum is 10. What's my minimum?
0.
0. What's Q1?
5.
5. The median?
6.
6. Q3? 8. Good. Okay. So you guys got this.
The box is lined up with a number should go.
Yes. So very important part of a box plot is the number line. Okay, and that's where you find. That's where the box plot gets its values. Okay. Am I messing something up? No.
Is that an outlier on top of it?
Yeah, this is an outlier over here.
Okay. So
At
that's
0.
something.
Okay. Are there any outliers? Yes, 0 is an outlier.
Mr. Chen,
Yes.
so in order to get the mean, you would add the 5, 10, 15
I'm sorry?
for the, it says here for the mean.
The
You just
mean.
add those numbers up to get the mean.
Mean is an average.
Balance point.
Okay, then
So there's no mean in this equation. right?
there's no mean being displayed here. Okay, there's no way for us to find the mean here. This is a number line. These are not values. They're not data points. Okay, this is a box plot. All of our data is represented in the upper part. This down here is a number line, and they're not data points. Yes.
So in the last equation, the minimum was 1, and then this one is 0.
Yes.
I don't understand why.
Okay, well, I just erased that one. Okay. Here I have, what would you think the minimum should be here?
Well, in the other one, the grandchild's age was 1.
Yes. So here I did not give you the raw data.
Oh,
Okay. So I'm just giving you the box plot and I'm asking you to draw these conclusions from the box plot. Okay. So the box plot shows a circle here, or a dot, at 0. Right? So that's part of the data, and that would be the smallest value in our data set. Okay? If this wasn't here, what would be our minimum?
3.
Our minimum would be 2, because the whisker goes down to 2, and that would be the smallest data point that we have. But we have a 0 here, and that it's an outlier, but it's part of our data still, so our minimum is 0. Is that okay?
Yes.
Okay.
Thank you.
Any other questions? Okay. I have to talk about numeric summaries for spread. Okay. We have the range. We have the interquartile range. And we have, our interquartile range is abbreviated IQR. And we have the standard deviation. And then, okay, the range is just equal to the maximum minus the minimum. And the IQR is equal to Q3 minus Q1. So looking at our data set over here, what is our range and what is our IQR?
Our range is from 2.
Maximum minus.
No.
This is the maximum minus.
Range.
The range is the maximum, which is 10, minus the minimum of 0. I have a range of 10. The IQR is 8 minus 5, 3. Okay. So from a box plot, you should be able to identify the min, the max, median, Q1 and Q3. And once you have those numbers, you should be able to find the range and IQR without any issue. What do these things mean? It's nice. We have these things called range. We have the IQR. They give us an idea of the amount of spread in our numbers. Okay? And what I mean by spread is how similar are the numbers or how different are the numbers. Last week we talked about variability for a categorical variable. And we said, if we talk about race, the United States has more racial diversity than a place like Japan. Okay? And if we imagine what Japan looks like and what the United States looks like in terms of different races that we would encounter, there's more diversity or more variability in the United States than in Japan. Okay? Now, when we're talking about spread, we're talking about a numeric variable here. But we're still talking about the same idea of variability. Does our population look very similar to one another when it comes to this numeric variable? Or is there a wide range? Or is there quite a bit of variability? Okay? So if we think about the ages of students in a high school driver's ed class. Okay? So this is a numeric variable. Ages of students in a high school driver's ed class. Okay? Then think of the ages of people who vote. Okay? So just imagine running a polling place and you see a variety of ages there. Okay? Between the two groups, which one has more variability? The polling place, right? So that if we imagine the high school driver's ed class, how old will our students be?
15 or 16.
15, 16, 17, maybe you have an 18-year-old in high school that is taking driver's ed, okay? But that's pretty much it. You're only going to see 15, 16, 17, and 18-year-olds. You're not going to find kids much younger than that. You're not going to find people much older than that, okay? You talk about voters, what kind of ages are we going to see?
18.
Anybody from 18 to 100 years old, okay? Or however old, we're going to see a large variety of ages, okay? And so, in terms of spread, okay, these numeric summaries for spread will reflect that variability in the numbers, okay? So, we can, when we're talking about high school driver's ed versus a polling place, it's easy to see this group has lots of spread, this group has little spread. Okay, where we can use lots and little, or large versus small. Those are adequate descriptors because the distinction is very clear. Okay, but sometimes we want to be more specific. Okay, just like judging at the Olympics, rather than just saying, oh, that performance was great and that performance was pretty good. We want a specific number. We want to assign numbers to performances, and we can say this performance gets this many points, and this performance gets this many points. In the same way, numeric summaries here assign numeric values to the spread. And that way we can compare them directly and say this one has this much spread, and this one has this much spread. Okay, so all we're doing is we're taking what we understand about kind of the variability or variety of numbers that we see, and we're assigning numeric values. That's what the range does. That's what the IQR does. They just highlight different components of that aspect of spread. Okay. For example, if we're talking about the performance of a vehicle, different people might be interested in different aspects of the car. Depending on who you are, maybe the performance of a vehicle that matters to you is how fast does the car accelerate, okay? maybe for another person, the performance of a vehicle is how well does it perform in a crash test. Okay? These are two very different things, but they both talk about, quote, the performance of a car. Okay? The range, the IQR, and the standard deviation, we're all talking about the spread of a set of numbers, but they highlight different things. Okay? The range gives us biggest minus the smallest. It's going to give us a very kind of brute idea of the spread that is affected by outliers. The IQR, on the other hand, not really affected by outliers. Okay? And the standard deviation is another thing that talks about spread. And this is the way to calculate the standard deviation is more complicated than the range or the IQR, but it still gets us this idea of how much spread exists in our numbers. Okay? Do we feel okay about the concept of spread in our numbers? Okay, so easy. I'll just numeric summaries for spread. Okay, so spread describes how similar or different the numeric values are in a data set. So if we think of ages in high school driver's ed, class, little spread. The vast majority will be 15 and 16-year-olds, a couple kids who are older than that, and that's about it. Okay? Ages at a polling place. We will have lots of spread. Okay. And the numeric summaries will reflect that. Okay. This thing that has a little spread, the range will be like 3, and IQR will be like 1.5 or 1. Ages at the polling place, the range is going to be like 80, and the IQR is going to be like 50 or something. Okay, much bigger numbers. Same thing with the standard deviation. Standard deviation for the ages in the high school class, I'm just making it up, maybe 1.2. Standard deviation for ages at a polling place, maybe 20. Okay, I don't know. So let's talk about the standard deviation and calculating the standard deviation. What is the standard deviation again? It is a measure of spread. Okay? It just describes the amount of spread in our data set. And spread talks about how similar or different the numbers are. Okay. Is there a diversity when it comes to this numeric variable? Is there a diversity in ages? Yes or no? Is there diversity in heights? Yes or no? Is there diversity in whatever numeric variable we're talking about? Okay? That's what standard deviation is getting at. Okay. So one way to think about the standard deviation is think of the mean as a point, and then we're going to find distance from the mean. Okay? So if I say the average income in the United States is $50,000 per year, and you make $40,000 per year, what is the difference between you and the average?
10,000.
You're making 10,000 less than average, okay?
20.
What? Or let's say, and someone else on the other hand who makes $100,000 per year, what's their difference between average?
50.
They're making 50,000 more than average, okay? So, standard deviation, we can think of this as the difference from average, okay? But then we do something where it's not going to just be the average distance from average, but we're taking that distance from the average and we're going to square it, take the average of the squared distances, and then take the square root of it. So it's a little weird, but we're taking the main idea is we're taking the distance from the average, okay, we call that a deviation, and we're going to square it, average those, and then take the square root of it, okay? So we're dealing with the square root of the average squared distance, okay? But we can think of it as kind of the typical, you can think of this as typical difference from average. Okay, so to calculate this, I'm going to just list off some steps. Number one, find the mean, find the average. Okay, that's the average. Finding the mean, find the average. Number two, find the deviations for every point. Deviations from average. How do we find the deviations from the average? Huh? Just take the difference, right? If I said the average was $50,000 per year and you make $40,000, what did you do? You did 40,000 minus 50,000 is 10,000. Okay? All you're doing is you're just subtracting. So finding the deviations from average for every point, just subtract the mean from every point. And then we square the deviations. What does squaring mean? What does it mean to square a number?
Multiplied by itself.
Times itself.
You multiply a number by itself. Please do not say double it. Because I would just say we double the deviations, and that's not what we're doing. We're square them. We multiply a number by itself. So we're squaring the deviations. And then we're going to kind of find the average by adding up the squares, adding those up, add those up. And then we divide by n minus 1. Okay, so we normally divide by n to find the average, but we do something a little bit different. We just divide by n minus 1. Okay? But this part is kind of like finding the average. We add them up, and we divide by n. Okay, but instead of n, we're using n minus 1. And then the last thing is we take the square root. Okay. So can we do this? Well, let's try this out. Okay? All right, let's say there's two families, okay? Let's say we have the Addams family, all right, and the Smith family. Great, okay. All right, and let's say both families have 4 kids, but the average age, well, let me see. Okay, so the Addams family, their oldest is 16 years old, and then they have a 12-year-old, an 8-year-old, and a 4-year-old. Okay, so they methodically planned out each of their children to be 4 years apart. Okay. The Smith family, on the other hand, and then, so what's the average age over here? 10. Okay. So let's say the Smith family, on the other hand, they have a 12-year-old, 11-year-old, a 9-year-old, and an 8-year-old. Okay?
Same.
And what's the average over there?
10.
Also 10 years old. Okay, so both families, their average age is 10 years old. Okay, but what happened with the Smith family? They just had kids, boom, 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 right? Addams family, they spaced them out. Okay, so we can already see which family has more spread in the ages. The Addams family. Okay, in terms of the diversity of, you know, what kind of toys are they going to have? You're going to have like little kid toys and iPads, okay, or whatever, right? Stuff, okay? You're going to have all kinds of stuff. Maybe the oldest is into a gun, airsoft gun or something, okay? All right, whereas in the Smith family, you can probably get away with just buying like a couple big things that fit the age category and whatever, and everybody's kind of happy, all right? Maybe, maybe not, who knows? Okay. Depends if they're boys or girls, right? But anyway, let's say, so we already know that there's more spread in the Addams family and the Smith family, than at least when we're talking about kids. But let's go ahead and see what our standard deviation says, okay? And it should reflect what we know, okay? So let's find the standard deviation for the Addams family, okay? So step 1 is finding the mean, and we said the mean is 10, okay? Is everyone okay with that? You add them up, you divide by 4, you get 10, okay? So then, what do? We're going to find the deviations. So what do? I'm going to subtract 10 from each of these numbers. Okay? And what do I get? I get 6, I get 2, -2, and -6. Okay? Those are the deviations. And then I'm going to square these deviations. Okay? So step 3, I'm going to square the deviations. So what is 6 squared?
36.
36. 2 squared?
4.
4. -2 squared?
4.
4. And -6 squared?
36.
36. Is everyone good with that? Okay. And what does the next thing say I should do? Step 4, I add these up. So I'm going to do 36 plus 4 plus 4 plus 36.
72.
And I get a sum of 80. Okay, so add up the squares, add them up. And I get 80. So that was step 4. What's step 5?
Divide by
N minus 1. So what is n minus 1? 3. So I'm going to do 80 divided by 3. And I get 26.67. Is that right?
N is the total.
N is however, your sample size. How many numbers do you have? N is how many numbers you have. So this is, N is equal to 4, so we divide by 4. I mean, divide by 3. Divide by N minus 1 gives me 80 divided by 3. Okay. Is everyone okay so far? Anybody lost?
Can you go back to 5? Like dividing by n?
Divide by N minus 1. That's what I'm doing right here. Okay. So what is N? Listen up.
4.
4.
N is 4. It's my sample size. It's how many numbers do I have? How many kids are in the Addams family? There's 4 kids, so N is 4. So I divide not by 4, but N minus 1. So I do 80 divided by 3. And when you punch that in your calculator, you get 26.67. Okay. 667, 6667, whatever. How many decimals are there? The last one, what do? I take the square root. So what's the square root of 26.667? It's like 5 point something, 5.17. 5.164. So the square root of 26.67, 5.164. Is that good? Okay, so then I want you to go ahead and find the standard deviation of the Smith family. Standard deviation of ages of kids in the Smith family. That doesn't matter. I would say keep it here for decimals. I know in the diagram.
If you have a calculator, you don't have to generate. You can just leave it in the calculator.
All right, how's everyone doing? Good? We need another minute, or are we good? Okay, so let's find the standard deviation for the Smith family. I've got 4 kids. What's the average age? Step 1 is X bar, finding the mean. X bar is 10, right? The average age is 10. And I'm going to find the deviations from average for every point. Okay? So I subtract 10. And I see that the oldest kid is 2 years older than average. This one kid is 1 year older than average. This guy is 1 year younger. And this guy is 2 years younger. Okay, or girl. The next step is to square each of these deviations. And I get 4, 1, 1, and 4. Okay? So in this example, the numbers were all easy because we all had whole number deviations and it was easy to square. It's possible that you get a number with a decimal and you're going to have to subtract a decimal and then you have to still square the thing. Okay? But I hope you guys can do that just fine, right? It's just punching in a slightly different number. Then what do? We add them up, and what do we get? 10. Okay?
Divide by 3.
And then we divide by 3, n minus 1, so we get 3.333, or whatever we have. And then we take the square root of that, and I get 1.8257, or something like that. 1.826, either answer acceptable. Okay?
So that's the standard deviation.
That is the standard deviation of ages in the Smith family. Or at least in the ages of the Smith family children. Okay? And so what we can see already by looking at the ages in the Addams family, we knew that there was more spread and less spread over here. We can quantify that. And we can say the standard deviation of ages in the Smith family is 1.826. Compare that to the standard deviation of ages in the Addams family, which is 5.164. Okay? And there you have that. On the quiz next week, I might give you a set of numbers, maybe 4 or 5 numbers, and I say, calculate the standard deviation of these 4 or 5 numbers. You guys feel comfortable with that?
Yeah.
Okay, good. So you can practice that in your homework. Okay, so there's one last thing we can use with the standard deviation. Okay?